Welcome to the CoSpace Robot family. Today, we'll be introducing you to CoSpaceRobot GP. CoSpaceRobot is an official platform for both RoboCup Junior Rescue Simulation and RoboCup Asia-Pacific CoSpace Challenge. CoSpace Grand Prix is powered by CoSpaceRobot Studio. Apart from the CoSpace programming interface, it provides interface in Scratch, Python, and C. Please visit our website to find out more.
In this session, we will give you a step-by-step guidance to the CoSpace Grand Prix. We hope it will help you to have a better understanding in the CoSpace Grand Prix for beginners and to take part in the CoSpace Grand Prix Challenge U19 category.
Line following is probably the most common application in robotics. It is widely used in industries and even hospitals. If a robot can think, the thought process of a line-following robot will be very similar to that of a human being. And that can be simplified into 3 actions: sense, plan, and act. CoSpaceRobot will give you a unique first-hand programming experience in such applications. Let's take a look at the CoSpace Virtual Robot. It is equipped with one color sensor to sense the floor RGB color, which is a short form for red, green, and blue. One gyro sensor to sense the robot's orientation. One ultrasonic sensor to sense the front obstacles. And 6 infrared IR sensors for line tracking. What is the logic behind the robot's thinking process when it tracks a black line? The 6 IR sensors mounted on the robot are like 6 eyes of the robot. When the first left IR sensor, we call it L1, senses the black line, the robot needs to move forward. When the first right IR sensor, we call it R1, senses the black line, the robot also needs to move forward. When L2 senses the black line, the robot needs to turn left slightly. When R2 senses the black line, the robot needs to turn right slightly. When L3 senses the black line, the robot needs to turn left rapidly. When R3 senses the black line, the robot needs to turn right rapidly. This process repeats forever in a loop, and this will ensure that the robot tracks the black line. Let's code a line tracking program in CoSpaceRobot.
For optimal performance, your PC laptop should meet the minimum configuration. Let's watch a video guide on installation.
Hello, good job. We are almost there. Let's click on the Experience button to see if our computer is compatible with this software. While we are at it, let's also check and see the version of our software. It's always good to have the latest version. Awesome, it seems that our computer is compatible and our software is up to date. And now it's time to activate our software. So there are 3 options: Learn, Compete, and Experience. So for this example, we're going to use first steps. All right, we're going to click on Workshop Pack 1. The activation window has just popped out, so please make sure you're connected to the internet and input your account number as well as your serial code, which is also your license number. So these will be given to you via email, so please make sure to check your email. And also please make sure when you put in your serial code, there are no spaces in the front and at the back, because the serial code is case sensitive.
Double-click CoSpaceGP icon on your desktop. Now, choose the level and map, which is also known as the virtual environment. In this tutorial, we will choose Future City for illustration. To adjust the virtual environment, first, click anywhere in the virtual environment, and then, press the Q, W, E, A, S, D keys to adjust the 3D view. If you press Shift plus the keys, it will make the movement faster. If you mess up the environment, you need to click on the control panel, and then click on Ctrl plus H together to reset the virtual environment to the home position. To manual control the virtual robot, first, click anywhere on the control panel. And then, press the 4 arrow keys to move the virtual robot manually. While the robot is moving, the live sensor data will be shown on the control panel. Double-click on the CoSpaceGP icon on the desktop. Now, choose your level and map, which is also known as our virtual environment. For this video we will choose Future City Practice Field. We will use the CoSpace Grand Prix first steps as an example for illustration here. Double-click on the AI button to enter the programming interface. First of all, you will need to create a new project. Click on the New Project button. Please remember to give this program a team ID, a team name, a project name. Remember, once team ID and team name are confirmed, they cannot be changed anymore. However, you can change the project name if you wish. Based on the analysis earlier, we now need to convert the logic into code which the robot can execute. The first statement should tell the robot that when L1 senses the white line, the robot needs to move forward. Step 1. Let's create a statement named L1 senses white line. Step 2. After the statement name is defined, we will add conditions to this statement. We click on L1 until it turns white in color. This means L1 will sense for the white line. Step 3. We should tell the robot what to do when the condition is met. In this scenario, the robot should move forward. That means both wheels should have the same speed. Step 4. Finally, click on Preview button to see whether you have set the correct wheel speed. Great! We have completed our first statement. Repeat the 4 steps above to complete statements 2 to 6. Statement 2. When R1 senses the white line, robot moves forward. This is similar to statement 1. Make sure we have set the same speed for both wheels. Statement 3. When L2 senses the white line, robot turns left slightly. This time, we will set different speeds to the left and right wheels. As the robot turns slightly, the speed difference should be small. Same concept applies to statement 4. This time, the robot turns right slightly. Statement 5. When L3 senses the white line. This means that the robot is almost off track. So the robot needs to turn left quickly. This time, we can set the left motor speed to be negative and keep the right motor speed positive. Same concept applies to Statement 6. This time, the robot should turn right quickly. After we have completed our program, we should do a quick check that the logic is correct and make sure every statement has conditions and actions. Once you have completed programming, it is very important to save and build. Save means to save the most recent program that you have just completed. Build means to check syntax errors, create a C code and a dynamic data link file with extension DLL. Now you can click on the preview button to see how the robot will behave. If you wish to modify the program, click on the Stop button and you will go back to the AI panel to modify the program. Now, you can load the program which has been compiled as a DLL file using the Load button in the control panel. After successful loading, we can use the play, pause and stop buttons to control the robot's movement. We can monitor the robot's performance in the control panel. We can also change the viewing perspective from the menu bar. Choosing 𝗖cie_𝗦𝗍𝗶 front camera will let you to have a first-person view, or driver's view. Choosing 𝗖cie_𝗦𝗍𝗶 following camera will let you to have a helicopter tracking view. When the robot reaches the finishing line, it stops and the time it took to reach there will be recorded. Well done. You have completed the line tracking program. In the CoSpace Grand Prix U19 category, the system allows users to add self-defined variables. For example, we need to add a new variable called CoSpace. First of all, click on VAR button in the AI panel. Secondly, give a name to the new variable. Then, set the initial value. Finally, click on Add New Variable button. The new variable is now added. It can be used in your program. You can also remove an existing variable. The CoSpace Grand Prix U19 platform allows you to use advanced conditions and advanced actions to enter less complex codes using C code convention. Open my first program in the AI panel. Now, let's remove the IR sensor settings from the graphical section and put it as C statements in the advanced condition. Trial run and monitor the robot performance. Again, let's remove the wheel speed settings from the graphical section and put it as C statements in the advanced action. Trial run and monitor the robot performance. We can see that the robot performance remains unchanged. Let's look at the line tracking logic again. We can use if-else statements to control the program flow. Now we can put this set of statements in the advanced action. Trial run and monitor the robot performance. Apart from the if-else statements, we can also use switch case statements to express the same logic. Before we start coding, we need to define a new variable called action. Let's write the line tracking program using switch case statements in the advanced action. Trial run and monitor the robot performance. Printf is a predefined function in C. By using this function, we can print data or user-defined messages on consoles or monitors. Let's see how to add the printf statement in our code. Open my first program again. Let's change the LED status for the statement 3 to 6, so we can monitor the change of LED status later. If we want to display both wheel speed and the LED status on our console, we need to add printf for each statement using advanced action. Trial run and monitor the robot performance. In CoSpace Grand Prix U19, the system can convert your graphical programming in C automatically. You can also write your code in C. In Challenge 1, you need to program the robot to travel on the speedway. During its journey, the robot must stop at each waypoint for 2 seconds with LED flashing, and then move away autonomously. On the speedway, there are purple-colored patches on the floor. We can use the RGB color sensor mounted on the virtual robot to detect the color of the floor. The RGB sensor is mounted at the front right corner of the robot, facing downwards. The RGB sensor detects colors. It outputs the exact color it detects, in terms of the red, green and blue light intensities. Each channel value can range from 0 to 255. Move the robot manually. Let the RGB color sensor sense the color patch. The RGB sensor gives 3 readings for each color detected. They are the corresponding red channel reading, green channel reading, and blue channel reading. Just like programming other sensors, you need to specify the range of all 3 channels of the RGB sensor values as the condition, then set the action to be taken when the condition is met. How can we program the robot to stop at the waypoint for 2 seconds and move away autonomously? We can use duration. The duration is a countdown timer. One duration is 25 milliseconds. So 2 seconds is equal to 80 durations. 2.5 seconds is equal to 100 durations. The basic idea is to program the robot to enter a 100 duration cycle when it senses a purple-colored patch using the RGB color sensor. That's 2.5 seconds. The robot will stop for the first 80 durations, or 2 seconds. The robot will move forward for the rest of the 20 durations, or 0.5 seconds. Here is the code in GUI. When the robot senses the purple color, both wheels will be set to 0 for 100 durations. The robot moves away with both wheels' speed set to +30 for the last 20 durations. This speed setting is to ensure that the robot can move out of the purple area within 0.5 seconds. In CoSpace Grand Prix U19, there is a gyroscope to sense the robot's orientation. The gyroscope is mounted on the virtual robot. It senses the robot's orientation. The gyroscope comprises of the tilt sensor and compass sensor. There are 2 variables associated with the gyroscope. The rotation x gives the degree of inclination. The range of rotation x is from -90 degrees to +90 degrees. Rotation z gives the direction. The range of rotation z is from 0 degrees to 360 degrees. Just like programming other sensors, you need to specify the range of rotation x or rotation z in the condition setting, then set the action to be taken when the condition is met. For better performance, you can let the robot have different speed when it moves up and down the ramp. Please program your robot to complete the task. The sample code can be found in PPT slides. Well done. Let's work on Challenge 2. In Challenge 2, you need to program the robot to travel in a smart city. During its journey, the robot must stop at each waypoint for 2 seconds with LED flashing, and then move away autonomously. Let's analyze the map carefully. First, the robot needs to make a U-turn at the first waypoint. It will move forward at all other waypoints. Secondly, the robot needs to make a 90-degree turn when it senses pink, if the robot is on the left-hand side of the field. The robot needs to move forward for a certain period of time when it senses pink, if the robot is on the right-hand side of the field, to avoid the zigzag road. Thirdly, the robot needs to make a U-turn when it senses cyan. Therefore, we need to define 3 variables, after first station, RHS, and U-turn on cyan. During the journey, the robot needs to make correct decisions based on the information received. The robot also needs to make a 90-degree turn to avoid walls. An ultrasonic sensor is mounted at the front of the robot which can provide the robot with distance information. The ultrasonic sensor is mounted at the front of the robot. It senses the front obstacles and provides feedback in cm. When the robot moves forward, we can monitor the live feedback data on the control panel. To program the ultrasonic sensor, you have to specify the range of distance as a condition, then set the robot action to be taken when the condition is met. How can we make a proper 90-degree turn? We can use the compass sensor, similar to the earlier example. When the robot is close to the wall, it has to make a 90-degree turn. We will let the robot enter a 120 duration cycle as an example. The robot will keep turning until it has turned for 90 ± 2 degrees. We will then end the 120 duration cycle by setting the duration to 0. The robot will move on to its next action. Here is the code in GUI when the robot is close to the wall. Both wheels will be set to +10 and -10 respectively for 120 durations. The robot will keep turning until it has turned for 90 ± 2 degrees. The duration will then be set to 0, the 120 duration cycle ends. We use the modulo operator here. Please program your robot to complete the task. The sample code can be found in PPT slides. Well done. Let's work on Challenge 3. In Challenge 3, you need to program the robot to travel in the Eco Garden. During its journey, the robot must stop at each waypoint for 2 seconds with LED flashing, and then move away autonomously. You can take Challenge 2 as reference, analyze the map and complete the code. The sample code can be found in PPT slides. Well done. You have completed all challenges. Let's move on to the CoSpace Grand Prix Online Challenge. Let's work on the CoSpace Online Challenge, or as we call it, the iCool Challenge. Double-click on the CoSpace GP icon on your desktop. First of all, you need to select the correct level. Then select iCool Challenge tab. Choose the challenge map you will be working on. Analyze the map and complete the code. We will use the CoSpace Grand Prix first steps as an example for illustration here. Save and build. Load the DLL from the control panel. Click on the Start button and monitor the robot's performance. When the robot reaches the finish line or when you click on the Stop button, an ICS file will be created. The ICS files contains the code, result and robot trajectory. Save the ICS file and send it to the event organizer. Congratulations. Well done.
RCAP CoSpace GP Challenge Rules U19 category. This category is for students aged 19 and below. Welcome to the RoboCup Asia-Pacific RCAP CoSpace Challenge. Automation of routine tasks is currently a concept that interests many industries. Among the most revolutionary parts of it are autonomous vehicles. These are visions of the future of city infrastructure. The main ideas they all share are self-driving cars and shared mobility. Those are set to revolutionize the ways we navigate through cities. In CoSpace GP Challenge, teams are required to build a real robot, develop and program appropriate strategies for both real and virtual autonomous robots to navigate through both real and virtual worlds. For the iCool challenge, participants need to program an autonomous car to navigate in a smart city. The autonomous car needs to pass multiple waypoints before reaching its final destination. In this smart city, there are roads, buildings, color markers, black and white lines, ramp or bridges, apron tags, and waypoints. In the iCool challenge, there will only be a virtual robot. The robot has an IR sensor array, an ultrasonic sensor, a RGB color sensor, and a gyroscope. Students need to utilize the elements in the smart city to plan the best path and program the robot accordingly. Let's take a look at the game process. The duration of the game is 8 minutes. That means the robot has to complete the whole journey within 8 minutes. At the beginning of the game, the virtual robot is placed at the start station. When it travels towards the finish line or end station, the robot must pass all waypoints in any sequence. It must stop at each waypoint for 2 seconds with LED flashing, and then move away from the station autonomously. The game ends when the virtual robot arrives at the finish line in the virtual world. If the virtual robot passes all waypoints and reaches the finish line, the team rank is determined by the race time at the finish line in the virtual world. If the virtual robot is not able to pass all waypoints, regardless whether it reaches the finish line or not, the race time for the virtual robot to reach the last waypoint will be recorded. The team rank will be determined based on the number of waypoints passed, followed by the race time.
The detailed rules can be found in RoboCup Asia-Pacific official website. If you have decent experience with programming or have completed CoSpace GP first steps or are above 12 years old, CoSpace GP U19 is designed for you. There will be 2 videos in this sharing and highlighted games section.
Everyone, I am 𝗖់_𝗦𝗲 from Singapore, participating in the CoSpace GrandPrix Challenge U19 category. I started doing robotics in March this year. While programming my robot, I used 3 different strategies. The first one is path planning, which is used to decide the best path to take. I screenshotted the map and drew out several possible paths, considering the PID stations, color markers, the number of turns, and distance, as these factors can significantly affect the speed of the robot. After deciding on the best route, I will still make minor changes to the path to achieve greater stability. The second strategy I used is soft coding, where I create functions that will be called upon to carry out actions when certain conditions are met, and also variables that can help to keep track of the position of my robot on the map. This is especially useful for actions that need to be used repeatedly. The examples are line tracking, turning when facing a wall or detecting certain colors, U-turns, and stopping at the PID stations. Last but not least, I used hard coding, as my routes included some shortcuts that do not provide any sensor inputs for my robot. To achieve the optimum output, I did multiple runs and measurements. Through the process of trial and errors, I was able to obtain some values for me to directly write into the codes and let the robot run a designated route without sensor inputs. In preparation for CoSpace, I tried out all the practice maps. The first 2 maps looked manageable. However, when it came to the more difficult maps, I encountered problems sometimes, even when I followed the tutorials step by step. I started considering more possible scenarios and tracking the values in debug to adjust conditions or add on more statements, such as color range and more cases for line track. These changes made me realize what worked in theory will always need to adapt to fit the physical environment, and I must consider many other factors to make sure the car not just runs, but runs consistently. To challenge myself further, I attempted to code in C, which is a programming language I have never learned before, and implementing proportional integral derivative control on line tracking parts of the robot. I never truly understood or coded PID before, but CoSpace gave me the chance to grasp this concept firmly. Even though I didn't get to use it in the preliminary round due to instability of high speed, the experience of learning it is rewarding beyond what I can imagine. It taught me to be resourceful, search for answers on different engineering websites and ask a mentor. It taught me to have perseverance, debugging again and again to make sure the codes will run smoothly. It taught me patience. The best values can only be obtained after a tedious process of tuning the PID. In addition to technical skills, I also learned the importance of communicating and sharing ideas with my mentor and fellow participants. Through good communication, we improved faster, solved problems more creatively, and rejoiced in progress together. A participant I would like to learn from is 𝗖cie_𝗦𝗃𝗍 John Henry. He mentioned in his presentation video that he used different speeds for different parts of the map and also increased turning speed. These are things I did not think of when programming my robot, and I think that these are certainly important factors that can make a remarkable difference in speed and timing. With this enriching experience, I will share my learning with my fellow members from the Robotics Club who will be participating in virtual RoboCup Asia-Pacific GrandPrix as well.
I'm a game changer. I'm a risk taker.
Hi everyone, my team ID is SG3010 and my team name is Roger. From the team ID and the team name, you can probably deduce that, number 1, I'm from Singapore, and number 2, the only member in my team consists of this guy named Roger. I'm honored to be making this presentation for all of you, and I hope that the little bits of knowledge that I'm about to share with you will be useful and worth your time and attention. I have done some CoSpace robotics before, because prior to this, I participated in the iCool challenge. Now, the category I'm participating in is the U19 Grand Prix. The basics for doing Grand Prix can all be found in the guiding videos that were emailed to us at the start. So the problems that I've investigated that I'm going to be sharing with you today are more regarding the optimizations for robots. These are not essential features in the sense that because any robot can still complete the tasks without these methods that I shall be sharing. However, these methods allowed me to cut down on my robot's runtime, so I'm sure all of you would appreciate it too. So the problems that I investigated are, firstly, how to integrate PID control into the line tracking code, and secondly, how to push speed while maintaining stability. The result is a better optimized run that is obviously more smooth. I'm sure everyone who has done the warm-up challenges and the preliminary rounds would know. The mission for Grand Prix is to find the fastest way to move from the start point to the end point, while passing through all the orange waypoints. The challenge task can essentially be broken down into 3 mini-tasks. The overall mission will be solved when these 3 tasks are put together. So the first problem that I investigated is how to integrate PID control into line tracking. PID control is a very powerful method for controlling systems, used often even at the industrial level. First, let me get some terminologies. What we call the ideal state is what we want to achieve. In our case, we ideally want our robot to be in the center of the line that it is following. So, being in the center of a line is our ideal state. Now, after we have established an ideal state, there will be error states. For example, when a robot is on the right side of the line instead of the center of the line, we call it an error state. Finally, a response is an action that can be taken to minimize the error states. For example, when our robot is on the right side of the line, we want to take the action of turning left, so the robot will travel closer to the center of the line, which is our ideal state. So the general idea of a control system is to introduce a response at the right time to achieve the ideal states and to avoid the error states. Now, PID control is just one special type of control system, whereby we decide the response based on how big the error is, which is called P control, and we also decide the response based on looking at how much the system has been deviating from the ideal state in the past, which is called I control. And lastly, we also decide the response based on how much the system is expected to deviate from the ideal state in the immediate future, which is called D control. Just in case you're wondering, why do we choose these three alphabets, P, I, and D? Well, they are not chosen randomly. I can tell you that P stands for proportion, I and D stands for integral and derivative, but it is beyond the scope of this presentation to go any more in depth than that. So if you're really interested, I would really encourage you to find out more about it online. Anyways, for my robot, I only used P control and D control. The advantage of PD control is that it allows line tracking to be a lot more smooth. In line tracking, the error is the distance of the robot away from the center of the line. This can be found by looking at the IR array readings in the CoSpaceRobot. For PD control, the response is decided based on the size of the error and how much the error has changed. In other words, how far away from the center of the line is the robot currently, and also how has the distance between the robot and the center of the line been changing across time. So what we want to do is we take the size of the current error and we multiply it by some factor Kp, and then we also take the current error minus the last error, in other words the change in error, and we multiply it by some factor Kd. Now, there are four different possible cases that we need to respond to. First is when the error is small and the error is not increasing. In this case, as you can see, the robot is in the center of the line and it's facing parallel to the line. In this case, we would want the response to be small. In other words, we don't want the robot to turn left or right a lot because it is going to go straight. In the second case, we see that the error is big, but the error is not increasing. As you can see, the robot is not at the center of the line. However, it is traveling parallel to the line, which means that the error is not changing. In such a case, we would want a medium response. We will want the robot to turn to the left quickly enough so it can go back to the center of the line, but not too much because it might overshoot, and instead reach the left side of the line instead. In the third case is when the error is small, but the error is actually decreasing. As you can see, the robot is at the center of the line, so the error is small. However, we don't want the robot to keep moving straight, because if it keeps moving straight, then it's going to overshoot and hit the left side of the line instead. What we want is for the robot to turn right by a medium amount instead. So it will end up moving parallel to the line. In the fourth case is when the error is big and the error is also increasing. As you can see, the robot is on the left side of the line, so the error is big. And what's worse, the error is going to keep increasing because the robot is facing away from the line. In this case, we want the response to be big, so the robot can quickly turn right and go back to the line. Another method that I want to share is to accelerate slowly to reach the top speed, instead of commanding the robot to run at a very high speed immediately. The advantage is that it will make the robot run a lot more smoothly. Otherwise, if I were to command the robot to immediately run at base speed of 95, the robot would often jerk to the side and move in a very unstable way that often ends up going off the line. The logic for acceleration is very simple. If the current speed is smaller than the targeted maximum speed, then increase the speed by 1. Otherwise, don't change the speed. A few tips for debugging is I start off with the robot at a very low base speed of 30 when I'm starting off the coding process. So I first try to make the robot complete the map. When that is successfully done, then I go on and try to increase the base speed. This saves me a lot of time in my debugging process because I can have the guarantee that any issues that arise during the speed up process occurs only because of this increase in speed, which causes the decrease in stability, and not because my code's logic has inherent flaws. I think I have achieved rather commendable results. If I were asked to solve the same challenge again, I would see if I can find even more ways to let the robot run faster. I have learned from coding a CoSpace robot with the GUI programming offered by CoSpace Robotics that coding isn't just about the syntax and the libraries and the functionalities of a coding language. What's more important is the pseudocode, the flowcharts, and the logic behind your code. I have gained experience on what to look out for when approaching a challenge task and how to look out for solutions. I have also gained enjoyment in being able to participate in robotics activities despite being in the middle of a global pandemic where most of my other activities are restricted. I hope everyone gets to enjoy the process of coding in CoSpace Robotics, and I hope everyone can take away as much knowledge and experience away from CoSpace. But most importantly, don't forget to have fun. Thank you.
After finishing CoSpace GP-U19, why not try CoSpace Rescue? Like to view more sharing videos? Visit RCAP Academy YouTube channel.